All right. So I think I can open up the chat window at the bottom just in case anyone can't see my slides, but hopefully that's all right. So I am going to talk today about the impact of retreating glaciers on water, food and energy security. And in my title, I've called this an anthropogenic hangover. And that's because a lot of this comes from legacy, things that we've already done, but obviously it has an impact in the next day as well. It has an impact in the future, and what that means for environmental quality. So just a little bit about kind of how I got to working on this. As Tavy said, I started off life doing my PhD in Aberdeen with a sort of secondment in Simon Fraser in Vancouver. And I was modelling superglacial and englacial hydrology at that point, both in the Greenland ice sheet and in Arctic Canada. From there, I went on to do a couple of postdocs at Stockholm University, again, looking at watery things, looking at ice sheet hydrology from a paleo perspective in that case, and also looking at how you can visualize that from seafloor morphology as well. So I've always had an interest in the sort of watery side of glaciology. But during my time in Sweden, a somewhat unfortunate event meant that I had an opportunity to start work on contaminants in glacial catchments. And that was via a plane crash in 2012 on Sweden's highest mountain, Kebnekaise, and a NATO Hercules shortly after takeoff from Norway crashed just below the summit of Mount Kebnekaise, and it dumped about 11,000 litres of fuel onto one of the glaciers there. And Stockholm University has a well-known research station that I'm sure many of you will have been to, Tarfala. And I was a visitor there anyway. Every year I was in Stockholm, I used to go up to Tarfala. And I went up there to actually try and help to understand how the pollutants from that plane crash were being stored and released from that glacier system. So that really gave me an insight into what I kind of thought of as being applied glaciology. While in the past, a lot of what I did was very much focused on theory, what I was doing there was really a chance to do something that mattered immediately rather than something that was predictive or trying to reconstruct something from the past. I moved to Plymouth in 2016 as a lecturer, and since then I've really began some really fruitful collaborations with some colleagues of mine who are more catchment scientists than glaciologists. But in doing that, that really opened up my eyes to different techniques, particularly some of the nuclear techniques I'm going to talk about tonight, and different approaches. And I've written here interdisciplinary, because I really think that interdisciplinary research just adds such an excellent dimension to challenges that maybe we haven't approached from these perspectives before. So that's been a real eye-opener for me. So the talk tonight is kind of in three parts. First of all, just to kind of refresh everyone's memory about glaciers as a freshwater resource. The past couple of weeks, we've had two excellent talks from Helen and Sridhar, focusing really on ice sheet scale Antarctica. And this is kind of bringing us back down to that smaller mountain scale. Part two, which is really the main component of the talk, is about contaminants in the cryosphere and how that impacts on water quality. And part three then moves on to how glaciers feed into the water, food and energy security nexus, and I'll introduce some of those concepts a little bit later. So we'll start off just with an overview of what glaciers mean in terms of freshwater resources. So they contribute hugely to global water security. And just those images I put up on the screen kind of reflect some of those key issues, be that drinking water, energy, agriculture, all of these things. Glaciers are really, really important for that. So what is water security? It can be defined as access to safe drinking water and sanitation. And it's obviously a key component of this nexus that I've mentioned already, and very much central to sustainable development. Now, we're living in a growing world, both in terms of population, but also in how we consume things, whether that's energy, food, or other resources. And because of that, there's increasing pressures on these nexus resources, food, water, and energy. But I would argue, and I think many people would argue, that water is probably one of the most exploited of these resources. And actually, even within that, about 70% of water abstracted is used directly for agriculture. So these things are really interrelated, and that's why we refer to them as the nexus. And that food production further complicates this idea of water security because of challenges associated with land degradation. And a lot of the work that my colleagues are doing in Plymouth, not so much from a glacial perspective, but around the world, in Tanzania and Chile and different regions, really looking at those land use practices and the impact on soil erosion and what happens to that sediment when it enters hydrological systems as well. And ultimately, about 30% of global energy is attributed to food production and supply as well. So again, really heavily interlinked between those three things. But coming back to the cryosphere, which is why we're kind of all here this morning, this afternoon, tonight, wherever you're joining from, how much do glaciers contribute? I've put in this funny, I think it's quite funny, this image, blue iceberg water, pure iceberg water from Canada, probably sold at some horrendous price. But forgetting about the sort of tourist gimmicks, how much do glaciers actually contribute to freshwater supply? Well, we know that the glaciers capture 10% of Earth's surface, but within that, that's about 70% of total global freshwater. So a really, really vast amount. And it can sometimes be easy to forget, particularly if we're not living in regions that are reliant on glacial meltwater, that literally hundreds of millions of people rely on fresh water for at least part of the year. And regions such as the Andes in South America and the Himalaya are particularly reliant on glaciers for their freshwater supplies. What I'm going to go on to talk about shortly, though, is not just the risk to downstream water quantity from changing glaciers and their retreat, but also the quality of glacier-fed waters. And that applies to both the sediment load in the waters linked to glacial erosion and bed load, but also the release of natural and anthropogenic contaminants that have been contained in these glacial catchments until they've melted out. So this is a really, really nice figure from Woodford Bytart. It's about contribution to domestic water use in irrigated land area. So the circles that you see on the left represent hectares of land in terms of irrigation. The light blue circles are where melt contributes between 45 and 100% of water for irrigation, and the dark blue circle in the middle is between 80 to 100%. So you'll see that Bolivia, which is the largest circles there, has up to 402,000 hectares of land that directly rely upon glacier melt for irrigation. And on the right-hand side, you see all of these eyes. They're either black or red. And the eyes that are black represent 1,000 people. Each of the eyes are 1,000 people. And the black eyes represent where people rely on glacier meltwater for between 45 and 80% of their domestic water use, and the red eyes represent where meltwater is required for between 80 to 100% of domestic water use. So in total, we've got over 500,000 people reliant on glacial meltwater for at least 45% of their domestic water supply. And in Peru, we've got about 150,000 or so that are reliant on it for at least 80% of their water supply. So these are really, really large numbers of people that rely very heavily on this resource. And that ties into this concept that many of you will have heard of, this idea of peak water. And it's a really nice image that summarizes that from Matthias Huss and Regine Hock's lovely paper from 2019. And what this shows is that as glaciers respond to climate, they shrink. But at some point, that shrink means that no more water can be produced than already has. So no matter how warm it is, not enough meltwater can be produced over a summer to exceed or at least balance what's been produced in the past. And that means that water supplies then start to reduce, particularly over the summer periods, and in places like the Andes during the all-important dry period as well. So that's a really brief overview of some of the sort of challenges associated with freshwater supply from glacier catchments. And I'm largely going to focus now on water quality as one of those challenges, and in particular contaminants that we find in the cryosphere. So there's been quite a lot of work done on contaminants in the cryosphere in the past. A lot of that is focused on things like persistent organic pollutants, some studies on heavy metals, and studies like those I was involved in Sweden that have looked at hydrocarbons and glacial environments as well. And glaciers are stores for any material that end up on their surface. So that's via atmospheric deposition for particularly small particles, accidents like I've already alluded to, but also things like mass movements and anthropogenic activity, mining, all sorts of sources of these different contaminants. But it also includes contaminants that haven't been studied so much in the cryosphere, and one that I'm going to focus on in particular today is fallout radionuclides, or FRNs, as I'll refer to them within the text on the slides. So fallout radionuclides are a product of nuclear testing. All right, so I think I told you a little bit about Isfjells glacier, and I was just going to tell you about our sampling campaign. So when we went there in 2017, we took a number of samples from the ice surface, Cryokinite, from 14 different sites, and we also sampled the moraines, the proglacial outwash, and also took a lake sediment core, which was 38 centimetres long, to look at the temporal aspect of both sedimentation and contaminant release in the catchment as well. And all of these samples we took back to Plymouth and analysed by gamma spectrometry, wavelength dispersive X-ray fluorescence to look at major and minor elements. We looked at particle size and also bulk stable isotopes to give us an idea of the organic content of the various samples as well. So for those of you who've never maybe used gamma spectrometry, and I suspect that's quite a lot of you, I certainly hadn't before I moved to Plymouth, I had never heard of it. But my colleague Will runs a lab there where we specialise in sort of nuclear techniques for the environmental sciences. Gamma spectrometry works because gamma radiation is some of the highest energy radiation we have. And it means that if you put a sample into these detectors, this is a well detector in particular, it analyzes the gamma ray energy spectra that are emitted from individual samples that you put into this well detector. You have to leave it in for a day or two because some of the very small concentrations are hard to detect, and we want to make sure that we look for even the trace varieties. So what you get is a return curve of sorts, a spectroscopy curve that looks a bit like this one here on the bottom right of the screen. And these different peaks in the gamma ray energy are representative of different types of radioactivity, of different radionuclides. So this is what our lab looks like. We have a few different types of gamma detectors, but also XRF, which looks at sort of metal content and organic content. And we have a team that's working there and have lots of international collaborations that work in that lab as well. So it's a fantastic resource to have on site. The core was probably the most interesting thing to achieve during this field campaign. Nick Selms, who's also my partner and a glaciologist, came out with me. We carried this rib over a few sets of moraines, took the gravity core out to the middle of this proglacial lake, and quickly discovered, after an awful lot of hard work, that the sediment was just far too dense when the core hit the sediment beneath the water, and it just wasn't retrieving a core because we didn't have enough weight. So actually to take the core required a little bit of chilly work from me, donning some waders, having a bit of a safety rope because I was sinking up to my knees in sediment. But I did manage to retrieve a core and extrude the core at the site to bring back to look at the different layers. So that was a first for me. Something I hadn't done before in any of my glaciological career. So that was really a lot of fun actually. So to the main results already, really the sort of headline things they away, the nuclear activities that we found in the Cryokinite on the ice surface were up to 2 orders of magnitude higher than any that we detected from the other samples in the proglacial environment. And And that immediately tells us that there's something special about the cryokinite and how it accumulates these contaminants in comparison to the sediment sources downstream. And I don't really expect you to look through all of the numbers in this, but really what I want to highlight is this column here. This is the cryokinite samples, and these are different types of radionuclides. And if you just look really quickly, if you look at the top, this is lead-210, which is a natural radionuclide. In cryokinite, the maximum was 14,000 becquerels per kilo. But if we compare that to the samples from the moraines, there were only 73 becquerels per kilo at a maximum. So really the cryokinite, for whatever reason, was accumulating these at incredibly high concentrations. These box and whiskers plots show radioactivity, not in the cryokinite because it would just dwarf the rest of the activity. You wouldn't be able to see any of this detail if I included that on these figures, but this shows the sort of range of radioactivity levels found in the central forefield, this first column here, in the top portion of the lake core, and then down the lake core to the bottom of the lake core, in the moraine samples, the second column from the right in each of these, and the final column in the proglacial outwash. So that was sediment sampled actually in the braided proglacial streams at the forefront of the glacier. So the cesium-137, which is an anthropogenic radionuclide, that's something that's present based on fallout from Chernobyl and other nuclear sources, was found in the upper portions of the lake core. You can see that here, and at higher concentrations than other off-ice sources, so the central forefield and the proglacial outwash. So that suggests already that there's some enrichment of the sediment in the lake core, probably from transport of material from the glacier into that sink downstream into the lake, but also through direct deposition over time. And although I'm not looking at this in this talk tonight, something else we've used the cesium for, and Americium, which is another anthropogenic radionuclide, you can use these to date cores as well, which is something that we've done for the cores that we've taken from this site too. The deglaciated forefield has very low levels of fallout radionuclides for most of these different types, apart from potassium-40, which is a natural geological radionuclide, despite the fact that it was deglaciated before the weapons testing era, before Chernobyl happened. So you would expect some accumulation of forefield if all things were equal across the glacial landscape, but clearly they're not. The amount in the moraines also relatively low, except for these strange anomalies, which suggest that there might be some hot spots in the forefield where perhaps downwasting of the ice has deposited these more enriched sediments directly onto the ground surface in front of the glacier. And another type of radionuclide, this time a cosmogenic radionuclide, beryllium-7. So this one's from space rather than from Earth. And it has a half-life of, I think, only about 53 days. So if you find beryllium-7 in any samples, what it means is that that sample must have been activated relatively recently, so it's quite a young sample. And we found that beryllium-7 was only present where meltwater flow was recent and active. So that includes the proglacial outwash, where there's a lot of beryllium-7 in that, so that's something that we would expect. In the upper lake core, although not in all of the samples, and in the cryokinite as well, we found quite a lot of beryllium-7, which was a bit of a surprise as well. And that told us something about the age of the cryokinite within those deposits. So these are just spatial plots showing variability in the radionuclide concentrations across the surface of East Files Glacier and from the 14 different sites that we sampled from. These are the artificial radionuclide, cesium in yellow and americium in pink, and the circles are scaled based on the activity concentrations in each sample. The natural radionuclides, beryllium-7 and lead-210 on this image on the top right. And then also at the bottom here, we have the percentage content of nitrogen and carbon in each of the cryokinite samples. And what I would sort of point out immediately, particularly these natural radionuclides, correspond very much to the samples that are most enriched in organic content as well. And also the samples that tend to fall on the sunnier side of the glacier, so the side where we have more meltwater availability and perhaps more energy available for life to flourish as well. So that might tell us something about the importance of bioaccumulation for materials like these contaminants. So why do we think fallout radionuclides accumulate in cryokinite then? It's already been shown, there's a nice paper by Liz Bagshaw from Antarctica, that carbon and nitrogen has been accumulating in cryokinite there. So it's already been shown to be efficient at that. And what our research shows, and the research of a few other groups, has shown that the same is true for heavy metals, for example, and also for these fallout radionuclides. We think that they are released through ice and snow melt from decades previous, so having been deposited onto the surface, perhaps directly after Chernobyl, after those long-range atmospheric transport took place. And when that does melt, it means that meltwater can move downstream enriched with these fallout radionuclides and then interacts with this organic rich cryokinite, which then accumulates the fallout radionuclides directly from meltwater. So that links to this idea of the fact that it has beryllium-7 present in the samples. It tells us that those cryokinite holes are most likely young and that the sediment inside them must be somewhat mobile, because we still have the presence of a very short-lived radionuclide within those samples. So that tells us that it's a replenishment by a frequent meltwater supply moving through the cryokinite holes that's helping to accumulate these radionuclides in this material. Probably a very boring figure for most of you. If we had to look at principal component analysis as a type of statistics that looks at trying to explain the variance in a data set based on some of the different attributes of that data set. And we computed this based on the results of gamma spectrometry on particle size, and also the bulk stable isotope analysis, or the carbon and nitrogen percentage of the samples. And what we found, first of all, is that there appears to be a clustering of samples from the north side of the glacier. So that's the north side or south facing side, the sunnier side with more meltwater. But also the principal component analysis told us that area weighted particle size, but particularly the percentage content of carbon and nitrogen, so the organic content of the samples, it can explain between the two of these things the majority of the variance in the data. So that kind of gives further weight to the idea that the organic content, or the bioaccumulation potential in the cryokinite holes, is really important for that enrichment. So that was a sort of proof of concept study that we did a few years ago, but it really piqued my interest, and the results were a lot more exciting than I expected. I didn't think that we would see levels quite as high as we did. So it got me thinking that it would be nice to try and understand what this means, not just on a really local level, but also on a global scale as well. And to do that, I've been working alongside some fantastic researchers from Italy, Poland, Canada, all different parts of the world, who've also got an interest in this particular topic. And we've been looking at the extent to which we find these fallout radionuclides. So on this figure, if I just plot, the yellow circles are where we've had some of the large atmospheric weapons tests. The red circles are where we've had major nuclear power plant accidents, like Chernobyl, for example. And if I plot up these pink stars on this image now, what this shows is the sites that between us we've analysed so far for fallout radionuclides in cryokinite specifically. So we've looked at 17 individual sites so far, and that spans everything from mountain glaciers to ice caps and ice sheet settings, and across a whole range of climatological regimes, from polar to obviously temperate mountain latitudes. But we've also got other areas to look at in the future. We're hoping to go to Greenland, although that's coronavirus dependent this summer. Samples from the Himalaya that the British Exploring Society were very kind to offer to collect for me, and also samples eventually from South America, again, COVID-19 dependent at the moment. But this is just a brief overview of the glaciers that we have looked at, including the Forney Glacier and the Americium Glacier in the European Alps, a whole host of glaciers in Svalbard, Arctic Sweden, British Columbia and Canada, 3 glaciers from Iceland, Greenland, the South Shetland Islands and Antarctica, and the Caucasus as well. And then adding in more from Sweden, Greenland and Antarctica, the samples that have been donated very kindly to us from researchers at Cardiff University, samples from the Ladakh Himalaya, and hopefully samples from the Andes and from our next field campaign as well. So if we have a look at the global results, then I'm going to start with lead-210, which is a natural radionuclide. It's something that's natural in the environment. This is the probably the largest radionuclide that we see in terms of activity levels in the cryokinite, but perhaps not so worrisome in terms of human health as some of the others that I'll talk about shortly. But what we find, the fraction of lead-210 in cryokinite is up to 2 orders of magnitude higher, not just in what we find in the moraines, but also what have been found in the past in lichens and mosses. And people have been studying the uptake of fallout radionuclides in things like lichens and mosses for a long time because they're atmospheric feeders. They grow through their interaction with the atmosphere, which means that they are very, very prone to accumulating these types of contaminants. But what we're finding is that actually the levels in cryokinite are larger than have even been seen in those types of environmental matrices. The highest single value for lead-210 was on Isfalls Glacier in Sweden, and that's getting up to 14,500 becquerels per kilo. And you can see the spatial distribution, seeing that these sites in the Arctic, particularly Greenland and down to Antarctica, have the lower activity levels in comparison to sites perhaps maybe related to local geology or atmospheric conditions. So if we move on to artificial radionuclides now, which are what I guess we're particularly interested in, cesium-137, if any of you have watched the really fantastic Chernobyl drama series that was on recently, you probably have heard of this particular element. It has a half-life of 30 years, and Chernobyl was in 1986. So this is already decreased in the environment. And if you were around at that time, you'll remember that there were issues to do with reindeer and hill sheep farming in the UK, and the uptake of a lot of this fallout following Chernobyl into livestock around parts of the Northern Hemisphere and Europe in particular. But what Sweden is finding, and there's been a recent study by the Swedish government where it's actually offered to test wild boar meat that hunters have collected. And they found that actually some wild boar meat in Sweden still contains 10 times more than the legal limit for selling and consuming meat in Sweden, which is 1,500 becquerels per kilo. And that means that cesium in the environment isn't just a legacy issue, it's actually something that's still ongoing. And that becomes particularly important where animals rely on things like lichens and mosses that are very efficient accumulators. And obviously this is something that we see in Arctic environments as well. So again, the highest average value was up in Arctic Sweden. The highest single value for cesium though, absolutely massive, 13,500 becquerels per kilo in the Swiss Alps. And this is really one of the largest activity levels for any type of sample that's been measured outside of nuclear exclusion zones, just to give you an idea of quite how radioactive that is. To look at the sort of geographical spread in a slightly different way, here's another box and whiskers plot here with all of our different sampling sites. And I really just wanted to show clearly some of the slight anomalies here, and I think Iceland is what stands out for me. So I took these samples in 2018 from 3 different glaciers, Skaftafellsjökull, Virkisjökull and Falljökull in Iceland. And the activity levels are considerably lower than the other samples that we've taken from around Europe, North America and Greenland. So we still don't know exactly the reasons for that. We need to look at the organic content in more detail and do more analysis once we can get back in the lab. But initial theory is obviously to do with local processes, volcanic activity, and the influence of having so much ash in the environment and what that means in terms of the organic makeup of the cryokinite in Iceland. It's actually not that well studied, cryokinite in Iceland, so if anyone knows of any papers that I've missed that have worked on cryokinite in Iceland, I would love to read them, because it's a part of the literature that I've really struggled to find any background on. So please do drop me an email if you know of anything. The other radionuclide that we're particularly interested in, and we're actually surprised that we found this in some of our samples because it's a relatively rare anthropogenic radionuclide, is Americium, is a product of plutonium-241. It's produced through the decay of plutonium, which has a half-life of only 14 years. So that means that americium is increasing in the environment, unlike cesium, which is decreasing. And plutonium is different because it's more soluble. It's also a stronger alpha emitter. And if you remember your A-level or high school physics, you'll know that alpha radiation can be stopped with a very thin sheet of paper, for example. You can protect yourself in that way. But if you consume it, it's quite different if it's taken up into the food chain that way. So it becomes quite dangerous when it's ingested. So the values for this are much, much smaller, but more worrisome in the way that they can be taken up into the food chain. And that's something that some of my students have been working on. So some key results from that work are that fallout radionuclides are widespread across the global cryosphere, and I think we would not really have understood that fully had we not sort of built this really fantastic international network that's really been working well. It has exceptionally high levels of natural and artificial radionuclides, and that's well above both what we find in the proglacial environment, but also in things like lichens and mosses that have been known in the past to be particularly strongly influenced by atmospheric deposition. And the levels of fallout radionuclides found at most sites are orders of magnitude higher than those in other environments, and include, yeah, indeed, some of the highest levels recorded outside of exclusion zones, which is quite a startling result. So what are the impacts of this then? Realistically, it's interesting to find this in the environment, but it's even more important that we try and understand if there are any implications of this. Will it just be diluted enough when it's transported downstream that it's not a problem? Or could the levels be potentially harmful, particularly for things like sinks, like proglacial lakes that are increasing in terms of their number in the cryosphere as glaciers retreat, and they act as sinks for sediments and anything else that's flowing from the glacier into the forefield. So perhaps accumulation in those types of systems could be one area that might be problematic, particularly for aquatic ecosystems. Another idea as well, that different plants and lichens have been used in different parts of the world to monitor fallout radionuclides and their activity levels across the world. But the cryosphere is obviously one of the more remote types of environment that we work in, particularly regions. And vegetation, as we know, for any of us that have done field work in these areas, can be somewhat sparse as well. But cryokinite maybe could act as one of these long-term biomonitors of radionuclides in the same way that other plants have been used elsewhere in the world. So this work is very much ongoing. I've got a new PhD student, Dylan Beard, who's taking an interdisciplinary approach to this, thinking about the sort of socioeconomic impact potential for release of contaminants, not just fallout radionuclides, but other things in the cryosphere. I've had two really wonderful dissertation students working with me this year, undergraduate students, one of whom worked on actually doing sequential extractions or acid digests of cryokinite to look at how fallout radionuclides, how easily mobilized they are within the environment, within the food chain. So that was a really fantastic dissertation. And another fantastic dissertation from Emma Smith, who looked at different environmental and geographical influences on the different types of accumulation of fallout radionuclides, whether things like aspect, elevation, and these other things are important for the levels that we record. And just a sort of point for anyone that's really interested in looking at this type of work, and looking to move ahead with this in the future, I think interdisciplinarity is really, really important, but also looking to expand the database further, which is something we're obviously hoping to do in the coming years, depending on how easy fieldwork is going to be in the current global climate. So I'm just going to give special mention to a few people now. Giovanni Baccalo at Milan in Italy, Edita and Przemysl in Poland, Phil Owens and UNBC in Canada, a whole team of people that have been working on this at Plymouth, and also Joe Cook, Eva Paniepa and the British Exploring Society, who have all been really, really helpful in either donating samples of Cryokinite they already had from different parts of the world, or even collecting them on our behalf, which has been really helpful to develop that database. So this next part is not going to be as long, which is probably good given this like delay to the talk tonight. But I just want to kind of give an overview of another project that I've been working on recently and will continue to work on over the next couple of years, which is about the impact of glacier retreat on water, food and energy security, but particularly in the Peruvian Andes. So I mentioned this concept right at the start, this idea of the water, food and energy security nexus and that connectivity between these three natural resource systems, and how the pressures on those three things are driven by growing populations, urbanization, even things like changing diets and different trends in diets, and of course economic growth in the way that we use the land and extract things. So if we think about things from a nexus perspective, this allows us to look at the connections between these three key resources and look at that interrelationship between environment, society and economy. And again, interdisciplinarity is super important here, but we've found in our project, and I know that others have found this as well, that working alongside local stakeholders to help co-produce knowledge is really important to get buy-in to this type of work early on and to help influence policy strategies in the future. So to put this in a context then, in the Peruvian Andes, about 10 million people rely on glacier meltwater, and are very dependent on food produced on land that's been irrigated by glacial meltwater. The Rio Santa catchment, which is our study area, it's a very large study area, provides about 10 to 20% of annual river discharge from the glaciers there. But this varies quite substantially, and during the dry season, that contribution is often greater than 40%. And during periods of drought, up to 90%. So during those really dry periods in the region, that's glacial meltwater being by far and away the largest contributor to freshwater supplies downstream. And that's not just an issue for drinking water and irrigation, but Peru actually has this fantastic resource of hydropower, and around 50% of Peru's electricity is directly from hydropower. So obviously having a reliable supply for power is really important as well. And the Cordillera Blanca, the mountain range that contains the glaciers in this catchment, it's actually the most glaciated tropical mountain range on Earth. But over the last 40 years, we've seen about a 35% reduction in the glacier covered area. So we're already seeing some really big changes there that will obviously impact freshwater availability downstream. So our project, it's been called the Sigma project, it's a short name. We're trying to take a sort of nexus approach to looking at some of the issues in this catchment related to changing meltwater supplies downstream, to try and improve knowledge of water budgets in the region, particularly the connection between how things change upstream and what that means for people and environments downstream. And also to look at the sources and fluxes of not just water, but different materials through the system as well. So that includes sediment, which I would also class as a contaminant in its own right, but also things like heavy metals and fallout radionuclides as well we'll be looking at, but in a much more tangential way than we have on our project. And eventually the output of this project, we hope, will help to contribute towards building support frameworks to help mitigate against any future changes in the region, and employing payment for ecosystem service methods to help to do that. So what are some of the pressures then in this catchment in particular? Put food, water and energy on this figure, and around that we have things like crops and livestock, biofuels, hydropower, all the different things that feed into the nexus. But specific to the Santa catchment, we have 3 different types of pressures: environmental, social and hazards as well, that all compound some of the challenges that we're trying to learn more about in the system. So environmentally, of course, we've got climate change, which is one of the driving influences on glacier change in the region. Contaminants, both natural and anthropogenic, and importantly in this region, although there are obviously a lot of anthropogenic contaminants, the glaciers actually erode rock that is very, very rich in heavy metals, and iron in particular. So the release of those metals has obvious implications for water quality downstream. And that links into erosion and sedimentation too. In terms of social pressure, population change, land use change, and the way that farming is done in particular. But Peru also suffers from corruption at different levels. Geopolitical conflicts are common. And it's also somewhere that's undergoing economic growth. So there's a lot of pressure from a social perspective too. And then we have hazards, and in particular in the region we're looking at, glacial lake outburst floods are something that have been very well studied, and there's also a lot of adaptation to that already taking place within the Cordillera Blanca, and some of the proglacial lakes have already been dammed and have siphon systems, for example, to keep the levels safe to reduce the risk of these outburst floods. So these all compound some of these challenges. So the project's very much ongoing and obviously slightly delayed. I really should have been in Peru or just coming back from Peru pretty much now, but that didn't happen, unfortunately. But we have had one field season in November where a few members of our team from the UK went and worked with our partners in Peru back in the autumn. So we're still very much in the beginning of the project, and hopefully I'll be able to tell the sort of glaciological community more about what we've done later down the line, I guess, when we've got some of our samples back from whenever that next field season will be. But what we're looking to do is looking at abstraction, contributions from glaciers, of course, both now, in the past and in the future, but not just looking at that long-term variability, but also looking at event scale variability. So looking at short-term periods of drought, also the impact of El Nino events, which are really, really important for this region as well in terms of the climatology. So we'll also be looking at the various contributions from glaciers, rainfall and snowmelt, and the apportionment of those different things to downstream water flow. And also thinking about re-evaluating that concept of peak water that I mentioned at the start, this idea that once glaciers retreat to a certain point, they don't produce the same amount of meltwater to contribute to discharge downstream. But I guess there are a few things we need to think about when we talk about peak water. Are contributions from precipitation, snowmelt mixed up in peak water? Is it really just glacial water we're looking at, or does it look at all of these things? Where is the discharge being measured? Are we talking about average water? So it's trying to pick apart what we mean by peak water to make sure that then when you work with local stakeholders and water companies, for example, that you're on the same page, you're talking the same language metaphorically, and ensuring that we really understand what we mean when we talk about that concept. Another of our work packages is looking at basin connectivity and how that responds to the changing hydrology. So thinking about how those upstream pressures impact people downstream. So looking at where the sediment's coming from, where it goes, how that changes over time, and the same for contaminants as well. Now to do that, we're using something called sediment fingerprinting, which a lot of us working in the sort of cryosphere may not have done in the past. And this, again, I can thank my catchment science colleagues for introducing me to this concept. Will Blake, who's at Plymouth, has developed a model that's really useful for this. And essentially, it's a bit like clue. So think about Mrs. Peacock in the blue has a very specific blue fingerprint, and Miss Scarlet in the red has a very specific red fingerprint. And if we have a river catchment with two tributaries, one, we've got a lovely red land cover and the other blue. And if we sample sediments downstream and it's red, we know where that sediment's come from. We know which part of the catchment has contributed there. We know it was Miss Scarlet. If we sample downstream and we get blue, we know that we can attribute that to Mrs. Peacock and her farm upstream. But what about if it's purple and it's mixed? Is it from Professor Plum? Is it from a single source? It's unlikely. It's actually a mixture of sources, but trying to unravel the relative contribution of those sources is not straightforward. So using statistical models to help unravel that is a really useful tool. And that's where this sediment fingerprinting comes in. In reality, of course, the situation is much more complex than I've just set out, and we have a lot more different things to consider. So that's everything from geology and land use, elevation, aspect, different parts of the catchment, be that glaciated or non-glaciated. So actually the Rio Santa catchment that we're looking at is quite a complex catchment, and we're having to try and characterize all of those different types of parts of the system to then try and fingerprint downstream and try and understand the main sources of downstream sedimentation at different timescales. So Sally Rangecroft and Jess Kitch, who are the postdoc and PhD student working on this project, went out there in November and started their sediment sampling campaign all across this really large catchment in the Rio Santa. And we're hoping to take delivery of their samples very soon so that we can get on with geochemical analysis of those samples using XRF in the CORIF lab here at Plymouth. The other sort of work packages focus around contaminant fluxes, so that really comes back to what I spoke about in the first part of the talk. I mentioned here that we have these very melt-rich rock or heavy metal-rich rock in the catchment, including a lot of iron. And I know that in one part of the catchment there are two valleys that are parallel to one another. And one of my Peruvian colleagues told me that the pH of the river water in one was pH 7, and just literally next door in the next valley over, we had pH 3. And that's purely down to the natural ability. As glaciers retreat, they are eroding bedrock that is rich in this heavy metal content. So it's really important to understand that and how that varies across the really large catchment. So that involves a monitoring strategy, looking at river gauging and water and sediment sampling to try and look at that variability in space and time. And of course, to tie into our other project, we will also be looking at contaminant contribution from the glaciers themselves, including radionuclides, heavy metals, possibly microplastics, and thinking about those processes of atmospheric deposition and how that accumulates in the cryokinite. And the final thing we're really looking to do here, and we're working alongside some really fantastic social scientists in Peru to look at this particular part of the project, but it's a really important part, looking at co-designing the work that we're doing, particularly when it comes to policy and trying to come up with future strategies to mitigate against the changing water availability in the catchment. So we're doing as much as we possibly can, and particularly with restrictions on fieldwork and with workshops, for example, and any gatherings of large numbers of people is going to be a bit of an issue to overcome, but I think many of us on this call will be in the same boat over the next few months, trying to sort of come up with alternative plans for our research. And in addition to this work, Sally Rangecroft and I are also developing a sort of education-facing tool called Glacier Map, which will be a free online resource via ArcGIS Online, where school students or anyone publicly can come and map glacier change from satellite imagery in this particular catchment in the Cordillera Blanca, to look at glacier change over time and actually do something hands-on to try and experience that change So that's something that we're going to be developing over the next month or two. Ultimately, what we'd like to contribute to is development of payment for ecosystem service, which is an idea that people who provide any sort of ecosystem service, be that freshwater supply or something else, should be paid for doing so. And that produces financial backing so that you can actually improve environmental quality, for example, or develop systems to help mitigate against flooding or regulate supply, improve water quality, and all of these things. So this is quite a complex process. It's something that Peru has been trying to do, but there's been restricted buy-in, I guess, from different stakeholders. So it's really important that projects like ours, and there are another 5 projects funded by the same funding call, that they can contribute to that by communicating science as best we can, so that both local stakeholders and also policymakers can really understand the outcomes of our research. The Santa catchment, where we're working, is one of the best understood catchments in Peru. It has a huge number of research studies, but very few of those studies have really translated into any change on the ground. And I think that element requires a lot of hard work and working alongside both social scientists and local stakeholders. And again, that word interdisciplinary that I'm so keen on, I would reiterate here, that's just really, really important to try and actually action change based on the research that's being done in the catchment, and not contribute to research fatigue amongst the people that live there. So from that perspective, for this project, special thanks to Sally, who's the research fellow on the project, Sergio Moreira in Lima, who is our and Will Blake, who's our professor of catchment science at Plymouth, and also Nick Selms, who's at Plymouth Marine Lab and working with us on the remote sensing side of the project. And I've put up some details about how you can follow our project if you're interested in finding out what our activities are over the coming couple of years. So 3 quick take-home messages. The first is that glacier-fed water security is absolutely crucial to the water food security nexus, particularly for regions like the Andes, where we're working on our new Sigma project. Message 2 is that water quality absolutely has to be considered, not just quantity. It's no use having plentiful water supply if that water isn't palatable and there's nothing you can do to improve that. So that might mean having to come up with strategies to help remediate that water quality, but we have to know what that is before we can do anything about it. And the third message really is that some unexpected paths. And I think when I was doing my PhD and my postdoc and working with models, I did do some field work, but I was looking at really big picture stuff, very much theoretical work. And I loved it, and to some extent I would still love to go back and work on Greenland glacial hydrology. But actually I find that this has been really rewarding. It's something that gives you feedback quite immediately. You can talk to local people and they can understand concerns. They might not know the science behind it until you explain, but they might have seen some of the impacts of that already on the ground. So it's actually been quite a refreshing change for me to take on something that is that bit more applied. And I guess I would encourage particularly any early career researchers listening to not be scared to try a project that's completely different. I probably am a bit of a jack of all trades and master of none if you look at my CV, but I think the experience that I've gathered through looking at glacial hydrology on all these different scales does help give you an overview, a sort of geographical overview that can be really important. And collaborating obviously becomes really, really important. So hats off to all of the many collaborators that I've worked with on these projects and continue to work with. So I'm going to flag up the next talk, which isn't next week because EGU, or Free GU as I've been calling it, is next week. But Neil Ross from Newcastle University is going to speak in May on the Foundation Ice Stream Academy Glacier Complex back to Antarctica again, what we know and what we should find out. So that is the next talk. And I will finish on this slide just to thank some of the funders for this work. All right, great, thank you.